Let's take a look at problem number 8, where I want you to read it and try just parts A, B, C, and D on your own. Again, you don't have to write full sentences, just, notes, just answers for these is just fine. Pause the video to do so, then come back and we'll discuss. Okay, so hopefully you're sensing the running theme here. The first thing you always want to look at is what's being plotted. This is a velocity versus time graph. That's completely different from position versus time, completely different from acceleration versus time. This is telling you how fast the object is moving and in what direction the object is moving. And it says it's the motion of a person. Okay, so letter A, at what time does your speed go to 0? Well, this is a velocity versus time graph. So all we're doing is looking to see when does the velocity go to 0. So hopefully you answered at 1 second. Because at the time of 1 second, you can see it clearly crosses the axis there. That means that person's motion at that moment is at rest, instantaneously at 0. All right, letter B, when is she moving forwards? This can get a little bit trickier. The correct answer is from 0 to 1 seconds. And so some of you may say, well, wait a second, isn't the person going backwards here because the graph is decreasing? Well, here's where we have to really separate what the graph is doing versus what's happening with the motion, right? So is the graph decreasing? Absolutely. Is the person moving backwards? That's not what it says, right? Because this is a velocity versus time graph, and on a graph, it's usually implied that positive is forwards and negative is backwards. So to know when the person's moving forwards, all we're doing is looking to see when is the velocity positive. So from 0 to 1 seconds, this velocity is positive. And then by the same token for letter C, when is she moving backwards? Well, if you got it wrong, maybe pause the video and rethink it. But hopefully we're saying from 1 second to 3 seconds, right? So if positive is forwards, negative is backwards, all we're really doing is looking to see when are the velocities negative. So what's this person doing? Let's see if we can try to visualize this, right? From 0 to 1 seconds, the person is moving forwards because the velocity is always positive, but what's the person doing? The person is slowing down. So when time equals 0, when the problem starts, the person's moving forwards at 2.5 meters per second, moving forwards but getting slower and slower and slower until the 1 second mark when instantaneously she stops moving. And then what happens? From 1 to 3 seconds, notice her velocities start going negative. So that's just going to be opposite from however she was originally going. So now she's turned around and she's starting to go the other way. Negative direction, opposite from where she was originally going. But what's happening to her speed? Well, the numbers, the amount of her speed, it's getting larger and larger. At the 1 second mark, it's at 0, 2 seconds it's 2.5, 3 seconds it's 5, so she's getting faster and faster and faster, just in the opposite direction. Okay, so try to visualize that in your mind. So she's moving forwards, maybe she's like jogging and slows down, stops, turns around, and then starts speeding up in the other direction. That's what this person's doing. All right, how about letter D? At what time does she return to her starting position? Well, for this, you might want to do some calculations for it. Maybe some of you can sort of reason it out without calculations. But hopefully you got at a time of 2 seconds. So how do we figure this out? Well, position on a velocity versus time graph, how do we figure that out? Well, we just talked about that in the previous video. What's the connection there? We know that if you're given a velocity versus time graph to find some information about position, you're going to be finding area. But be careful. Area doesn't get you position, it gets you change in position. So let's break it down into some nice easy shapes. Let's go from the 0 to 1 second. From 0 to 1 second, we have this triangle. And if you find the area there, you're going to find her displacement. If you want to calculate, you can go ahead and do so. But let's just talk qualitatively. Yeah, that's what you would do. By finding the area, you find her displacement. And notice I wrote as a positive area. What do I mean by positive area? How can area be positive? Well, the area here is representing displacement. Displacement is a vector. Remember, these are all positive velocities. She was going forwards. That means she's increasing in position, right? So whatever you would calculate from that is an increase in position. That's a positive displacement. And then let's go from the 1 to 2 second mark. From the 1 to 2 second mark, we're again finding area. But remember, as I talked about in the previous video, it's not just any area, it's the area between the line and the horizontal axis. So some students get confused when you hear the area under, they start finding the area in this region here. That's not right. The area is this shaded in region between the line and the horizontal axis. That's the area you're considering. I only went from 1 to 2 seconds because look what happens. First of all, we have negative velocities. Because this area is sort of under the horizontal axis, that's what we call negative area. Because what was she doing there? Remember, she was now starting to go backwards. So from 0 to 1 second, she went forward a certain amount. From 1 to 2 seconds, she went backwards. And hopefully you can see, because you're all really good at geometry, that these two triangles are congruent, right? Whatever area this one has going forwards, this has the same area going backwards, and so at this point, however much she went forward, she's now negated that by going backwards, and at the 2-second mark, she's completely back where she started. Okay, so hopefully all that made sense. Now let's go on to part E, where you're going to find her displacement for the whole time interval, 0 to 3 seconds. And notice this one has the correct answer, so you know if you're getting it right. But notice also the space is split into 4 sections, just like it is here on my screen, because you're actually going to be doing it 4 different ways. Okay, so in one of the sections, like, one of these quadrants here, go ahead and try working out a solution to this, and you know you get it right if you got negative 3.75 meters. And if you got that right, well then go on to another quadrant, another quadrant, another quadrant. See how many different solutions you can find using different equations or different methods of attack here. Hopefully each time you get negative 3.75 meters, do as many as you can on your own, and then come back to the video and I'll go through 4 of the solutions. Alright, there's no particular order to these, so if I'm not going the same order you did, or if I one you didn't do, don't worry about it, but please do take notes, and so you can see how you have other ways to go about doing it, and then on your own go ahead and try it different ways. So one way to do it is by using the long displacement equation, delta x equals v naught t plus half at squared. Now, if you're just looking at the graph, you have v naught, right? When time equals 0, you know the initial velocity is 2.5 meters per second, great, and we have the time 3 seconds, great. What we don't have is the acceleration, and so this would be a 2-step process. It doesn't mean you can't do it, it just means you have to find the acceleration. There's all sorts of ways to do it. One way is to use our tried and true acceleration equation, vf minus v naught over t, and initial velocity, final velocity, again, you can just read right off the graph. The initial velocity, 2.5 meters per second. Final velocity, well, that's at the end of the problem. That's going to be negative 5 meters per second, where the sign on that really matters, right? Because remember, at the 3-second mark, she was moving backwards at 5 meters per second. So you can find the acceleration using this equation and plug it into the displacement equation to get negative 3.75 meters, which means she ended up 3.75 meters behind where she originally started. Okay. There's plenty of other ways to go about this. So another way is using delta x equals v bar t, which, to be quite honest, is one of my favorite equations because usually it's a lot easier to find v bar than finding other things, as long as the numbers are relatively easy. So how do you find v bar? Well, you're just going to literally take the average of the initial and final velocities, just add them up, divide by 2. But they are velocities, so sign matters. So again, initial velocity, 2.5 meters per second, final velocity, negative 5 meters per second. That sign really does matter. So when you put those numbers in, you get the average velocity, multiply by the time of 3 seconds, and again, you're going to get negative 3.75 meters. Other students may say, wait a second, in the previous video we made all those connections, and we just talked about that, right? So what we could do is we could find the area, just delta x equals the area under the graph, or really between the line and the horizontal axis. Now here we really have to be careful with the shapes here. So we got a triangle here, we have another big triangle there, where this is going to be some positive area, this is going to be negative area. So you can find the positive area displacement here, this whole negative area displacement there, and then put them together. You've got to do it sort of piecemeal, because it's not just one big shape, right? So you find the area there, that's a positive amount, find the area there, that's a negative amount, put them together, you should be getting negative 3.75 meters. Or, if you're really savvy, you can realize from part D, we just figured out that at 2 seconds, she's back where she started. So this area is going to match this one, and really then all we care about is this area from 2 seconds to 3 seconds. That's really all that matters. Now this shape is a little bit more complicated. It's the trapezoid, and to be quite honest, I never remember the equation for area of a trapezoid, so if you don't want to do that, that's fine. You can always just break it into simpler shapes. You should be able to see we got this nice rectangular shape here, and then a triangular shape, so you can find those separately, put them together to find the entire area from 2 seconds to 3 seconds, however you like to do it. And in the end, you should get negative 3.75 meters. There's one more way to do it, and that's not even using the time, using our time-independent kinematics equation, vf squared equals v naught squared plus 2a delta x, rearranged for delta x as vf squared minus v naught squared over 2a. Once again, you can just read the initial speed, initial velocity of 2.5 meters per second, final velocity of negative 5 meters per second. Again, you have to find the accelerations. This would again be a 2-step solution, and there's a couple ways to do that. We've already shown that you can just use our tried and true acceleration equation, or if you realize, hey, we're looking at a velocity versus time graph, we can make one more connection. What is acceleration on a velocity versus time graph? Why, it's the slope, right? So you find the slope of this line, just pick any 2 points that are easy to read off the grid, and then plug that in here to find the displacement. Hopefully, of course, if you find the slope of this line, you'll get the same thing as you do by doing vf minus v naught over t. That'll be one more check along the way, but no matter what, we should be getting negative 3.75 meters as the answer for the displacement. And so again, any of these solutions you didn't get to or you didn't realize how to do, just take a couple notes, write down some notes to yourself, and then try it again on your own.